So far in this section, every limit problem has been very straightforward, very easy. Just plug in the number and things work out and we get a final answer that makes sense. The example 6 and 7 are going to be a little bit different. They are going to be situations where plugging in the number does not work so nicely. So these are the ones that I've been talking about, and I'll be telling you that we're going to have a situation where the problem does not give an answer. These are the problems I'm talking about. So let's take a look at the first one. It says the limit as x approaches 3 of the quantity x squared minus 9 divided by x minus 3. So if I try to do what I did before and plug in the 3 into all the x's, what am I going to get? So let's test it out. So x squared minus 9 divided by x minus 3, and x is approaching 3, so let's plug it in. If I did that right now, I would end up with 0 divided by 0 again. Now, 0 divided by 0 is what we call in math an indeterminate form. So what does that mean, indeterminate form? It just means that we don't have an answer. So if you put a box around this one and you try to move on to the next problem, you would get 0 points for credit here. Because 0 over 0 is technically not a number. We call it an indeterminate form, and that's just a fancy way of saying that it can be simplified, it could be turned into an actual number. Now, unlike 5 divided by 0, for example, that one does not have an answer at all. It's always going to be undefined. 0 over 0 is what we call indeterminate form because it can be fixed. It can be changed. It could be rewritten somehow to give a number. And here's how we do that work. So it turns out that to fix the indeterminate forms in these problems, what you have to do is basically think about factoring. So for example, in this case, I have a fraction with x squared minus 9 on the numerator. That x squared minus 9 is actually a special pattern. That pattern is called a difference of squares. So we can rewrite the x squared minus 9 as x minus 3 times x plus 3. We did this in the review when we were reviewing the basic algebra skills, and we talked about difference of squares there. The denominator is already x minus 3, so we're just going to leave it. I'm just going to put some parentheses around it just for, for the sake of making it look like the one on top. Now notice how we have x minus 3 on top and x minus 3 on the bottom. So what we're going to do is cancel them out, and the answer turns out to be the limit as x approaches 3, and then there's no more 1s because 1 times x plus 3 divided by 1 is going to be just x plus 3. And that's the simplified version of the original problem. So this fraction simplified to be this fraction. At this point in time, we repeat what we were doing for the previous few pages. X is approaching 3, and there's an x right there. So we're just going to plug it in. So, plug in the 3 instead of the x. In this case, we end up with 3 plus 3, which is going to give us a solution of 6. So in this problem, what we're saying is that 0 over 0 is actually in reality equal to 6, kind of. So the moral of the story is this: when you're dealing with indeterminate forms, you cannot leave the answer as 0 over 0. You must try to factor the problem and reduce the fraction to lowest terms, then repeat the limit procedure. Now, I just want to mention something about notation that I haven't said yet. Notice how I do the problems. In this first problem, I start with a limit. The next problem does not have any x's, it just has numbers, so I don't write the word limit anymore because I just applied the operation. I just write the numbers and I keep writing the numbers until I get to the answer. Now, if you notice, it didn't work out and I ended up with an indeterminate form, so what did I have to do at that point? I had to restart the problem and fix it by factoring. So therefore, I start by rewriting the original expression or the original problem, and notice how I keep writing limit on this line. That's because I have x's next to it. So the moment x disappears and you replace it with a number is the moment we stop writing the word limit. So notice what happened on that line. I had been writing limit, limit, limit up until that line because in that case I replaced x with 3, so no more limit. The operation has been applied. So I just stop writing the word limit and I just write down the numbers, and I keep writing down the numbers, and that's it. There's nothing else to write down. So that's what I want to mention about example 6. Example 7 is going to be very, very similar, so I would advise you to pause the video right here and see if you can solve example number 7 just like we did with example number 6. Try to mimic the same steps. First, start by plugging it in because you don't know if it's going to work or not. If it works, great, move on to the next one. If it doesn't work, try to fix the indeterminate form that you end up with. So pause the video here and I'll give you the answer in a couple of seconds. So just like we did earlier, I'm going to start by writing down the limit as x approaches -4 and then x squared minus 16 divided by x plus 4. So at this point in time, I don't know if it's going to work or not, so I'm just going to plug in the x as -4. So -4 goes into the first x, and then we end up with -4 on the denominator plus 4. So this is always required because you don't know if the problem is going to be an indeterminate problem or just a regular one like we did in example 1, 2, 3, 4. So you always want to start by plugging the number in. And in this case, if I plug the number in, I get 0 on top and 0 on the bottom, which is an indeterminate form. So unfortunately, it means that we're not done. It means that everything we did here is kind of a waste of time. So we have to go back and fix it. So the good news is 0 over 0 can be fixed, and the fix is very easy. All you have to do is factor the original problem. So in this case, I have x squared minus 16 divided by x plus 4. All I have to do is factor either the numerator or the denominator, or maybe both in some instances. In this problem, all I have to do is factor x squared minus 16. Again, this is a difference of squares, so it becomes x minus 4 and then x plus 4. And that's the factored version of the numerator. I already have x plus 4 on the bottom, so I'm just going to put parentheses around it so that it looks like the one on top. And because everything is being multiplied, I can cancel the x plus 4 and the x plus 4 with one another. So by canceling the x plus 4s, I end up with the limit as x approaches -4 of the remaining x minus 4 times 1 divided by 1, which is just x minus 4. And keep in mind, our x is approaching -4, so let's plug it in at this point. So what do we get? We get -8. So -4 goes into the x, and it adds up with another -4 to give us -8. So what's the takeaway here? The takeaway is that if direct evaluation leads to indeterminate forms 0 over 0, the limit will still exist in some instances. And how do you find it? You will have to do some algebraic simplification, or maybe use a table, or maybe use a graph. Typically speaking, algebraic simplification is the best because that's the easiest, the fastest way. So basically just factor the problem or do some algebra and then cancel out some things and you get your final answer. Okay, so direct evaluation or direct substitution is what we did on the first line. It's where we plugged in the number to see if things work, and sometimes they work, sometimes they don't. It just depends. If it doesn't work, like I said, factor the problem, reduce it, and then plug again.